And we are live.
So, welcome back, everyone. And the next session is by Sandeep Reddy Mallu on hunting mosquitoes in satellite imagery aided by deep learning. Yes, you heard that right. And I'll let Sandeep head over. But just as a way of introduction, Sandeep is he leads the analytics practice at Gramener. And I'd be remiss to say if I did not mention that he's also head of talent. So do feel free to get in touch with him. Over to you, Sandeep.
Thank you, Jaydev. Hello, everyone, and very nice to see you, everyone. This is me, Sandeep. I'm just going to turn off the camera to ensure we have a better audio. So here we go. So on a Sunday afternoon, you could have done any other thing, but you chose to attend this session. So I want to thank each one of you who made time to attend this session. So this talk is about a project that we had done for an NGO based out of Vietnam. The work essentially spanned across 9 months, and I would try and cover the complexities as well as the challenge and the outcomes that we have delivered on that particular engagement in the next 30 minutes. So let's start off with a few warm-up questions. How many of you have been bitten by a mosquito in your lifetime? Show of hands in chat would do. All right, we have a bunch. Jaydev, one question. Can speak up, or it's only chat is that they can answer?
Only chat for the duration of the talk, Sandeep. Later, we may allow them to unmute them.
Okay, so sure. I have a set of questions. So would you mind sharing any responses you get on the chat, please?
I will, yes.
Sure. So let's start with the first question. What do you think is the lifespan of a mosquito from birth to its end of life? Any guesses? All right. Do we have any on the chat?
Few days.
Nice. Oh, that's pretty close. On an average, a mosquito lifespan, once it comes out of the shell and it perishes, it's 7 to 9 days. Similarly, let's look at what is the lifespan of a satellite that spins in the geospatial orbit. And that's today, it's around 15 years by design of satellites. Some of the satellites also operate for beyond their lifetime, planned lifetime. And the last one, can you name some of the diseases that are spread by mosquitoes? So,
Popular vote. Chikungunya.
Nice. One. Chikungunya. There we go.
Well,
we have
malaria,
dengue,
obviously.
Malaria, yellow fever, mayora. There are a bunch of these that are today spread by mosquitoes. So a common pattern that we notice that globally, be it whichever part of the 7 continents, you notice that there are prevalence of mosquitoes, and wherever mosquitoes are present, the chances of they spreading diseases which are spread through mosquitoes is pretty high. And today, the story we're going to talk about essentially is that mosquitoes breed in water sources wherever they are, stagnant water. Then we will look at how do you take satellite images and process them using Python as a software programming language. We would look at what are the open sources that we have been able to tap into to aid our engagement. We used OpenStreetMaps exhaustively. Then how do you build a deep learning model that can help you process satellite imagery and also answer some of the questions of how can I identify where mosquitoes prevalence is high and act upon them? And the last part is any data science engagement needs to solve a problem, which means you have to have an output. You have to process the data and have an output and then translate that model output into a consumable answer. So how do we do that? This is what the story is for the next 10 minutes. Quickly talking about the different diseases and the burden of mosquito-borne diseases globally. Close to 400 million people get infected with dengue every year. That's a very high number. And this population is disproportionately in low-income neighborhoods across the globe. And close to 84 countries have the spread of Zika. When Zika had come on to the news cycle a decade ago, it spread with rapid pace. 84 countries have recorded on confirmed Zika cases. Then at least 40% of the...
This question, it is confirmed that Zika is spreaded.
Correct.
Okay.
That's the prevailing truth, prevailing accepted truth. Let me be straight on that. And 40% of the world's population is at risk of contracting dengue. This is in spite of the confirmed cases. There is a potential for larger population to get affected. And every 4 minutes, there is a reported case of chikungunya. This is the spread with which the mosquito-borne diseases have an impact on. And globally, though it is not talked about more, with so many people getting affected, the likelihood of deaths resulting in complications from these infections is close to 1 million deaths globally. This is the broad estimate that WHO has at the moment. Now, how do we fight this disease? There are a bunch of ways you can fight the disease. Earlier, we started with looking at the life cycle of a mosquito. The most common approach taken to kill mosquitoes is spraying insecticides, DBT, DT, across the board wherever you can, and hope that mosquitoes die. And in areas where you have waterborne still water sources, you spray any of these petroleum-based products like kerosene, so that the eggs that mosquitoes lay, they no longer stay on the surface, but they sink in and they don't hatch. These are the different approaches that are taken. One of the approaches that was taken by an organization called World Mosquito Program, they looked at how do you tackle the problem in a more logical manner. As in, when a mosquito lays its egg, the incubation period of that egg from the time the larva, the shell is created to by the time it breaks the shell and comes out, it's a 2-week period. So, and the mosquito shelf life is only a week. So instead of attacking the mosquito's life cycle of 7 days when it's actually active, they looked at, can anything be done about the mosquitoes before they're born? That's how they approach the problem, with the help of genetically engaging these mosquitoes in labs and introducing a bacteria called Wolbachia into these mosquitoes. This is where a mosquito is essentially bred in the lab, and it's inserted with Wolbachia bacteria. What the bacteria does is, essentially, once a mosquito has Wolbachia in it, this mosquito, be it male or female, when it's released into the wild, which is essentially into the larger population in a city. And when this mosquito that has Wolbachia starts mating and amplifying its population within that geographical region, slowly the number of mosquitoes that have Wolbachia starts increasing. So over a period of time, the population of mosquitoes, it still exists. You're not killing the mosquitoes, but you're ensuring that the mosquitoes will have a bacteria called Wolbachia in them, so that they do not contain the ability to transmit the diseases like dengue, Zika, malaria through mosquito bites. Typically, the way mosquito bites happen is a mosquito would bite a person who has these and sucks the blood. It would again go one more person, bite it, and that's how the transmission of blood-based diseases would spread. Now, what is Wolbachia? It's not some process that has been invented. It's an existing bacteria that is part of nature, and it's non-toxic to the human eye, smell, eye, or skin. So you are not affected by the bacteria. It is only affecting the mosquito's ability to transmit diseases. And it's environmentally sustainable because we are not impacting or changing how mosquitoes are bred. We are only sitting on top of their existing life cycle and introducing a bacteria into the larger population. And it essentially reduces the spread of diseases. This is the key takeaway that the approach has. World Mosquito Program bet on an approach essentially ensuring that how do I release mosquitoes which have Wolbachia into newer regions, so that those regions do not have spread of mosquito-borne diseases. One of the first test sites for Wolbachia-based mosquito rearing was in northern Australia, where in a 10-year period, when Zika used to be a most prevalent mosquito-borne disease in that region, northwestern land in Australia. In a 10-year window, when WMP program in consultation with the local governments, they started releasing these bacteria mosquitoes. North Queensland, that's the name of the city. And if you start noticing it, entire region after this is how the mosquitoes are brought from the lab in these boxes. And at every 50-meter distance, the box is opened and the mosquitoes are released, so that the mosquitoes do not have a longer distance flying span, because various conditions like winds, temperature, rain, they can't travel more than 50 to 100 meters. So there is a activity that has to be done at every 50-meter region for you to open up one more box and release mosquitoes. This is how the activity happens. And when this activity was done in periods of yearly cycles, and if you notice this chart, the number of dengue cases which were locally transmitted just crashed after a point in time. From the time the threshold of mosquitoes having Wolbachia within that ecosystem has increased to a threshold, you notice that after subsequent weeks of this point of inflection, the dengue diseases transmitted locally came to zero. This is kind of impact that the approach of introducing Wolbachia bacteria into the ecosystem creates within the into the local population. This approach, which has been wildly successful in North Queensland, Australia, is what WMP program is trying to expand to 18 more countries globally, which is close to 700 million people who can be impacted. How do they do it? They essentially look at find a site. You scope a site where you want to release this mosquito. How do you do that? You identify which city, in those cities which are the densely populated regions, and within this, which of the regions where you can expect more mosquitoes to grow. So be it low-income neighborhoods, places around water bodies, places around nalas. This is how you identify them. Then you set up essentially infrastructure to ensure you regulate the process. You have to work with local population. You have to work with local municipalities, governments to ensure that you have permissions to actually do this. It means you have to go through a long planning cycle for ensuring that you can release these one. Once you do that, then you specifically have to again order these mosquitoes that have Wolbachia and have to be bred in a lab, which means they take more time. It can't just be a easy way to catch these mosquitoes. You have to invest money, time to grow them, get them to the release locations and release them properly. Then you release them surgically. You identify which street. If I'm walking on, say, MG Road in Bangalore, I'm just making this up. How is that the right road to release mosquitoes? I see a lot of buildings there, but do we have people there? Or do I go to Cubbon Park? Or do I go to any other place? This is how you have to make these plans about where to release. And then finally, once you release these mosquitoes, you have to come back after a threshold of period, say 6 months, 9 months, come back and check the incidence of dengue or any other diseases that you want to tackle and see whether the spread has increased, decreased. That's the exercise that they do. Now, in all this exercise, there are a bunch of challenges that WMP had to go through. The first one is people issues. Can you have enough number of people who can do all these things for you? Because it's practically boots on the ground. And you need to have different kinds of specialists to do these exercises. It has a team of skills that have to come in. And given these are NGOs, ability to invest time is limited and money is all the more limited, which means you cannot take this kind of skill or idea to larger population. You have to pick and choose which region to go to first. Which brings to the next problem, which is how do you choose release sites? Let's say you identified a region, say Mumbai. Within Mumbai, where do I go and why? And is there a site large enough to make an impact? And if you miss human population, let's say you go to a downtown, which is a business district, and you do this exercise, but if there is no large population, does it even make sense? How do you avoid such problems? Or you go to a place like Powai in Mumbai. Powai is a big lake. If you release mosquitoes there, does it even have an influence? Each of these decisions are tough. And on top of it, all the government data that you have when you work with governments to say you have to release, none of these information is current. So you have to do ground truthing where you have to send people to actually walk down streets and talk about, okay, there is enough population here and there is enough impact of these diseases based on mosquito presence, and you have to make these decisions. Each of these complexities ensures that you will not be able to expand your reach for a larger region. And how does technology enable that to identify the specific sites? So the problem that we have been looking at is to look at how do you identify these sites for release at a faster clip, enable them to do a better job at planning, expedite the release of mosquitoes so that you have impact sooner, hence you can repeat the cycle faster. Now, in North Queensland, the entire cycle took them 10 years. With technology, how do you shrink that? That's the primary goal that we have been working with. So what's the missing piece? Now, in order to do site scoping, you have to have ability to understand the region in 100 meter by 100 meter region, because mosquitoes once released, they can't travel more than this distance. So how do you ensure you have these regions within a city that these is the right place? And mosquito population is not directly a proportion to the human population. It is not directly proportional to the buildings that exist. So how do you adjust for existence of buildings versus existence of population? This is a challenge you run into. And then you have to have accurate records of population in each region. Census, like in India, is done once in a decade. So population information is not accurate. How do you tackle that? This is where we looked at other parallel sources of gridded population world information. This is a globally accepted population counts, which is at a 1 square kilometer area, it gives out population. So how do you take this and make granular decisions? Each of these, when we got into the engagement with this NGO, we started looking at the rhythmic tune of combining our skills with Python, our understanding of satellite imagery, GIS capabilities, and then deep learning modeling. All these together is what has helped us to solve for this problem taking the first step of logically tackling this problem in a programmatic way, in a repeatable way with low cost and more certainty. And we call that as a perfect synergy that took 9 months of hard efforts from our team. Let's see how it was done. Step one was processing the satellite imagery. We worked with different open source service providers as well as commercial service providers to capture imagery of 11 different sites globally, spread across both Europe, Southeast Asia, and Australia. And we tried to get imagery of these specific regions of AOIs in 512 by 512 grid sizes and at a resolution of 50 centimeters at zoom level 18. To identify the satellite imagery, we worked on these imagery to be processed in cloud entirely. So we had to piggyback on COG structure and build a spatiotemporal asset catalog so that the querying becomes faster, and then relied on the different libraries of Python that acted as an enabler, like Rasterio, RioCogs, GeoPandas, SuperMercando. All of these libraries, which do one specific portion of work into the entire pipeline building, have come into play for us to process the satellite imagery, which was step one. Once the satellite imagery was processed, essentially what we were able to accomplish was take an imagery that was provided by these service providers, ensure that the satellite imagery has less cloud cover, has multi-bands that we need for the modeling, like RGB plus NIR bands, and ensure that the regions are accurately captured and the recency of the photograph. Satellite imagery is very expensive. So if you want an image that is very recent, 2-3 days ago, you got to pay a lot of money. So we had to piggyback and work with satellite imagery that was at least a year old, not too old, but at least a year to 9 months old. So combining all these and doing the processing is essentially what brought the satellite imagery from its raw form to a form that can be fed into the model. These were the different satellite providers that we looked at, Landsat and Sentinel, and then commercially we looked at SkySat, Worldview, and Comstat. Bunch of these were a combination of we procuring imagery for different regions with different providers, because no single vendor would have their satellite roam over that region as we want. So we had to go back and work backwards from an archive. Then the step two was using satellite imagery. How do you identify whether there is a building in an area of interest or not? We looked at this aspect of the problem by identifying the footprint using a deep learning model. This model relied on a unit architecture. In terms of the training models, we piggybacked on the OSM OpenStreetMaps data for building tagging, spent time in labeling some of the regions ourselves. All this data was fed into the model, and the model essentially gave an output which would identify different building patterns. There are a few drawbacks in this approach I'll cover once we get to the end of the talk. The third step was, now that we have a region, we know the building footprints based on the model output, and we have the GPW population as well at a 1 square kilometer region. And we also brought in the NDVI index for that region by calculation to ensure that wherever there are open areas, playgrounds, open areas, public tracks, or highways, we do not want to release mosquitoes there. So how do we exclude them? By calculating the NDVI values for these grids at 100 meter by 100 meter, we ensured that we avoid regions that had high NDVI values, and anything that is zero, which means there is no vegetation but there are buildings, you focus on them for release. This is how essentially the combination of the output from all these exercises would look like. A region of interest would have the entire region broken by grids of 100 meter by 100 meter chips, and each of these grid would get a scoring in terms of what is a potential population in that particular grid. So this essentially would give the planners a quick view of, in an entire region, which of the regions have population based that are higher in terms of proportion, so that in order for you to do release planning for the entire region, I would rather stick with a specific set of regions to cover a maximum population or geography. Now, let's look at two other quick representations of this output. On the left, you see an image of the satellite. This is how the satellite imagery would look like. And then when you have the population that is identified at 50 meter by 50 meter, this is how the grid map would look like. On top of it, when you combine with NDVI values, you distribute the GPW population from 1 square kilometer to 100 meter resolution, the grids on the bottom right corner. This is how the satellite imagery is finally presented as an output with layered data of NDVI, GPW data, as well as building footprint. All of them layered on top is how you would see the outputs. This is what is used by the planners for identifying release cycle. How did we get to this point, and what does it evolve? A quick view, this is how the overall solution would work. All the explanation I had done in terms of once the input imagery is identified, the data preparation exercise that goes in terms of ensuring you identify the different parts for train tests and validate for the deep learning model. You take OSM data and self-labeled data and feed into the model and get a gridded map out. The model identifies different building footprints, and that layer of different footprints, which is a GeoTIFF files in COG format, is taken up and layered with population density to ensure you get granular representation of the entire region in small chips of 100 by 100 meter, and each of them is graded for population. So the darker the color, it indicates that you have a higher population density in this region in that particular chip. Using this output, we further enhance this output to ensure we also assist in what is the right path or the fastest path to achieve a larger impact. So the second exercise that we had done post facto was essentially to look at performing a clustering, spatial clustering exercise on each of these chips of 100 meter by 100 meter and identify clusters of these chips so that the planners can identify which cluster should be approached first, second, third, so that you cover the maximum population instead of following the conventional approach of the roads that are there in the city. Using this clustering approach essentially ensured that you could minimize the number of trips you had to make and also maximize the impact that you can create. Now, all this application model building is a one-time activity. If you notice, the satellite imagery does not change frequently. Neither the population information doesn't change frequently. So all of this information is put through the entire pipeline that we have built, the data pipeline, the modeling pipeline, the output pipeline, is exposed as a web API. The outputs are essentially exposed as a web API, and the web API is what is integrated into the WMP's internal planning system so that a planner could look at a city, and once this model is run, the output is available. You could look at, I want to understand, I want to query this city and look at the population count only for a particular AOI, if I give the contours, or I want to identify of these chips that have been created 100 meter by 100 meter, what is the top 20% population, bottom 20% population, how do I identify them quickly? And grid-wise, you could make the calculations of grid-wise buildings. How do I get to the grids that have the highest building presence? The API that was created essentially to query this data would allow them to run all these simulations through without having to do any ground truthing. Compared to what the current approach was before we started working on this process, any planning exercise took anywhere between 3 to 4 weeks and needed on-the-ground volunteers to go validate all these parameters. Each of these has been replaced with model running, and we are in a position to assist the exploration exercise at a faster clip. So some of the highlights that we want to call out from the work: the effort savings that happened in the specific part of planning. The exercise essentially has brought down activity that used to take 3+ weeks to less than 2 hours. This is essentially the benefit that we have been able to deliver to our end client. Please note that this effort saving is essentially on the step. For this step to be successful, the model has to be run in a new region, so that still accounts for some effort. Second, the effectiveness of the outputs. We have taken the model and run it over 7 different cities where WMP has been performing. And across these, we have a 70+% accuracy of how the recommendations of the model are, and when that was compared against ground truth, which is a very high ROI. If you look at conventional approach which WMP had, it was a hit or a miss. You spray and pray. That was the approach. You didn't have a way to effectively measure this. But given the model's output and their on-the-ground truthing, now they have a way to actually start establishing the effectiveness, which means they are able to establish a data-driven baseline of model performance, which they can reliably bat for subsequent regions that they would go to. And there is a higher efficiency that you bring into the whole process because you already have these grids where you have button, and these grid information is available and exposed because of the way the GIS information is available. When subsequent audits are run at grid level, you could start comparing those results against the model. So there is a post-release monitoring benefit as well. That is what the WMP team gets from this solution. Now, if you look at the key learnings that we had on areas that we could have done things better. The GPW data is at a 1 square kilometer region, which is very high level. Our ability to restrict it to 100 meter by 100 meter has some gaps because we made the premise that buildings that have the centroid within a chip of 100 meter by 100 meter would account for the highest population. We did some approximations in that fashion when we brought down from 1 square kilometer to 100 meter population distribution. There are errors to be happening. We have achieved a set of metrics, but there is always scope for improvement. Then procuring satellite imagery has been a very big challenge. The reason, out of the 9-month exercise that our team has done, close to 6 to 6.5 months was spent on getting the right satellite imagery, processing it, validating whether the imagery can be funneled to the pipeline. That was one of the key learnings that we had. We presume that satellite imagery would work like any other data that can be fed into deep learning model. Turns out it's not that simple or easy. It's a lot more complex. That's our learning. The deep learning model's output, given that we are talking about building footprints and the training data that we have used is OSM data, which is again not independently vetted, but it's independently sourced, we had noticed that the model's performance essentially is in cases where it's a crowded place. Even a 18-wheeler cargo trailer truck would be identified as a dwelling, or a car that is like a Innova, which is longer, is identified as a small dwelling. So there are potential possibilities to refine the model and improve the model as well for the building footprint. NDVI did a calculation again. There are limitations on how we have performed the calculation. There are better ways and more sophisticated calculating approaches, which we have not taken. And the last one, the output grids. There is very likelihood that in case of large buildings or installation or complex housing complexes, they do not fit in a 100 meter by 100 meter chip itself. They are spread between multiple chips. In those instances, the challenge has always been that how do you distribute the population, and how do you ensure that the chip that we say has higher population is accurate on the ground? And because we did not have a way to measure the height of the building, we didn't have a way to approximate the population density of that particular building, because from the satellite imagery with a tilt angle of not more than 15, it was not possible for us to estimate the height of the building easily. So that's one output that is ripe for improvement. And the last one, the spatial clustering exercise that we had done, we used a bunch of clustering approaches, close to 3 of them. And depending on the premises that you make for these inputs, the clusters could be different. So we have not been able to come back with certainty that this is the only clustering approach that you should use. So we have offered the client a couple of clustering options. Now, on top of all of this, that brings us to the end of what I have planned from a narration standpoint. Now I'll switch text and actually show you how the application would look like, and give you a walkthrough of this. If you could give 1 moment. There you go. So what you see is a satellite imagery of a city of Asuncion. It's a capital of Paraguay. And when we started working on this particular city, the first step you do is you identify the boundary of this city so that you know these are the in the region. What are the regions I break down by test, train, and validate, so that for the deep learning model to understand which part of the city do I focus on from a training standpoint, where do you validate and where do you test, you have an exercise that you do. After that, we looked at what is the OSM footprint available in this city. Turns out the OSM footprint was reliable for dwellings only for this small region, if you notice. And then we had to work on identifying, in addition to the OSM footprint, we added our own manually labeled data and then identified a larger footprint of the entire region to understand the building footprint. I'm representing only a small region of the model output because of the nature of the file size. Putting the entire region would hang the system. So this is how the model would identify regions and their building footprints. And if you notice, wherever there are open areas, the model is clearly intelligent enough to understand that these are open areas and you should not tag them. And this is how the intelligence of the model starts building in. After this point, this step 2 would be looking at the GPW data that we talked about. This was a data that we talked about in terms of population density of this particular region at a 1 square kilometer chip or grid region. And if you notice, southern part of the Asuncion city is what has the highest population, and the northern and central parts are thinly populated, and then a cluster in the northeast. This is how the population data is available. After overlaying that information with NDVI information, which is essentially looking at normalized difference which you to index, you notice that the areas of green is where bulk of the vegetation is, and other areas there is no vegetation, which is an indication for us to look at which areas to avoid when making the final recommendation. All these data is combined together, layered, and the final outcome that you get is this. Each region is broken down into chips of 100 square meter. Let me zoom in a little here and take a look at some of the regions. If you notice,
So Sandeep,
the chip in,
sorry to cut you off. You are just 1
please.
minute left.
Done then. So this is how the output would look like, and the clustering would essentially give us clusters like these, so that the planners can look at which regions to go and spray first. So thank you. Be happy to answer questions.
Yeah.
Thanks a lot, Sandeep. But I don't see any questions on the stage. Feel free to ask them, folks, as we speak. Sandeep, I myself had a couple of questions. Oh, okay. It seems like Sashidhar has a question. He's asking, is the training data you have used to train the model challenges in generating the label data?
Let's take the city of Asuncion, for which I showed the representation.
Am I audible?
We looked at, yes, Jaidev, you're audible. Jaidev, I can hear you.
Please go ahead. Did you hear my question?
Yeah. Yes, Jaidev, I did hear the
Sorry
question.
about that.
So in case of Asuncion, for one city, we start off with OSM data for a little over 27 chipsets, close to 20,000 dwellings is what we started with. In addition to that, we added 10,000 more labels of building footprints. That was the entire data that was fed into the model for Asuncion city. So close to 30,000 dwellings in 18 different grids in the city. That's the starting point. The biggest challenge for us was to validate the data. We invested significant amount in labeling the data, but even the OSM data, to validate that the data was reliable, we had to do one pass with all the OSM tags as well. So I would say we spent anywhere between 21 to 24 days of effort by 2 people to getting the label data right. I hope that answers the question. Jaidev, any other question?
Thanks a lot, Sandeep. I think we are almost just exactly in time. Okay. Feel free to send any more questions towards Sandeep in the lounges. Sandeep, if you could stick around, that will be great. And meanwhile,
Sure.
if our next speaker is set up, we have our next talk on Python for the tuning of scientific instruments by Anirban Gupta. So, are we ready?